Okay, I'm Everett. I'm from Runtime Verification. We are a security firm. We do a bit more than security, but that's kind of, that's a hot thing to do right now, so we do security. And we have just completed an audit with Blockswap, actually. I think we're wrapping up the final details um, of that kind of these past few weeks. So kind of figuring out. It's a long report, so we have to kind of, go through and make sure all the I's are dotted and the T's are crossed. So just full disclosure, I didn't do the audit, and I'm not an expert on Blockswap, Stakehouse, all this stuff. But I'm going to talk a bit about our auditing process and what we do, how we helped Blockswap kind of achieve a higher level of quality assurance, basically. So just overview of the talk. Just going to talk a little bit about who RV is, what is blockchain security, why do you care? I mean, I think most of you probably already care about it. What are vulnerabilities and faults in software, and how do we detect them and mitigate them? And then I'm going to talk a lot more about like the structure of this audit report in particular, which I don't think is public yet, but it'll be public, sometime in the future, and you guys can go through it for yourself as well, get an idea, and maybe use this video as a guide for how to read it. Yeah, so just a little bit about runtime verification. We were started in 2010. Broadly, we're a software quality assurance company, so we used to, work with things that move, so planes, trains, cars, space shuttles, stuff like that. And that was a lot of like embedded system stuff, C programming stuff, and it wasn't really focused on formal verification as it was on just kind of fault detection at runtime or stuff like this. So more just monitoring of the monitoring of runtime systems, and then trying to detect when faults happen and either halt execution or go to a fail-safe mode or something like that, right? But more recently, starting in 2018, we started kind of getting into blockchain because it's a really good industry for software quality assurance in general, and it's really good for our technology to apply there. So that's kind of why I'm up here speaking to you today. Our approach is generally to make a mathematical model of the virtual machine that we are working with. So in this case, the EVM, we make a mathematical model of that, and then we try to prove that programs are correct with respect to that mathematical model. Yeah, so that's RV. Formal verification is a technique that you guys probably hear a lot about, or it's kind of almost a buzzword at this point. But what is formal verification? Well, generally it's where you try to prove that code is safe or code is correct, or that it's doing the right thing, or you try to prove that your system is correct or something like that. So a property you would want to formally verify would be like two trains on the same train system in Amsterdam won't head-on collide. There's no way that the train system would let them head-on collide. And you would want to formally verify this because you just want that to never happen, and it's worth the money to make sure that that never happens, as opposed to just testing it by running a bunch of trains and observing, oh, okay, like the trains haven't collided yet, so it's probably fine for the rest of all time. Used to be, like I said, we were in the embedded system space, so that was like robotics, yeah, public transport, aerospace, and now we're getting more into the blockchain space, so that's a lot of the time what that is DeFi protocols, so dApps and stuff like that. And there we're building mathematical models of these protocols and trying to verify that the code implements them faithfully. Why is blockchain such a good place for formal verification? Well, to be honest, like before blockchain, doing commercial formal verification wasn't feasible. It was too expensive. It's a really time-consuming technique, takes a long time. But blockchain, the smart contracts are pretty small. They have, non-trivial logic, so it's worth verifying. It's not like just a simple summation or something like that. They have pretty complicated logic, but the contracts themselves are small, so the code sizes are manageable for the tools that are approaching formal verification. So in the C world, or in the embedded systems world, we were dealing with code bases that were like millions of lines of code, and there it's not really feasible to do formal verification, but here in smart contract world, it's more like thousands of lines of code, so a bit more feasible to do that. And then also the other big thing is, like, there's a lot of money at stake, right? So if there's a reason for someone to hack something, like, they could get a bunch of money or they could get prestige or something like that, then they will. So that's kind of why we think formal verification is a good fit here. Yeah, so blockchain security, well, it's security in general, actually, but blockchain security has some specific things about it. But the key thing is that it's really profitable to think about how you could attack a system, right? So I could be a hacker, sitting at home, and I could, spend all year, 4 hours a day or something, kind of relaxed schedule, trying to find vulnerabilities and thing, and I only need to find one really good vulnerability that pays out, and that would be enough to fund my whole year of doing that, right? So there's a lot of pressure, there's a lot of incentive, I should say, for people to kind of be continuously looking for these exploits and, you know, trying to exploit them and get the money. And there's a bunch of different avenues for doing this, and not all of them are related to the system itself, right? So the first two are the kind of the ones we focus on, which is design vulnerabilities. So that's the actual design of your protocol. And then the second one is code vulnerabilities. So that's going to be bugs in your code. But the other ones are kind of, you know, unique to the specific situation. So trying to trick someone into giving them your private keys or some sort of phishing email or a scam or something like that. But those we're really not focused on because that's, you know, it's not really our expertise. But there are companies that focus on those things. It's just not us. So what is the design vulnerability? A design vulnerability is where the protocol itself is not sound in some way, right? So just simple, it would be where, you know, all the code is implemented correctly. It faithfully implements exactly what the white paper says. It's just that the white paper's design allows for runaway inflation or something like that. Or if you think of, you know, some government that takes their fiat currency and they say, I'm going to peg this at a ratio of 28:1 to the dollar, but that's not actually the market rate, that 28:1. Well, this is a design vulnerability because they're opening themselves up to arbitrage opportunities, right? So the thing is here, you have some specification of how the system is supposed to behave, and that specification is just unsound on its own, right? There's no way for that specification to operate safely. That's when you have a design vulnerability, right? And these are actually usually the more critical vulnerabilities. These are where you get, you know, runaway inflation of style events or things where suddenly the value of a token crashes to zero or the auctions can't keep up with the liquidations that are happening or things like this. So I have a couple of kind of silly examples on the slides if you want to look at those, but they're maybe not as interesting. So how do you mitigate design vulnerabilities? Well, it's, you know, you put time into it. That's basically what it is. You sit there and you think about the design for a long time, right? But the first thing to do is you make a specification. So the specification, you know, is going to start out something kind of informal. It's going to be like a white paper or something like that, and then you need to iterate, and then someone's going to say, but what about this case? What about this case? And then you have to think, oh, the specification doesn't cover what to do in that case. Okay, so then you add in the specification what to do in that case, and you keep doing that over and over again until you land at a specification that no one can really find a problem in, and it kind of seems to cover all the cases, right? And now you need to show, okay, you know, and you want the specification, it's important for it to be kind of human readable, right? It needs to be something that you can digest and hold in your mind, and you can think about, okay, is this consistent, and kind of like, you know, really play with in your own time. So that's why diagrams and stuff like this are really helpful. Another thing you can do is you can get an audit. So you basically have a third party do this, right? The third party comes and you explain your specification to them, and then they think like, oh, okay, what about this case? And did you think about that? And did you do that? And, you know, maybe we should prove this. And, you know, they go through and they look for sort of issues in your design. And then the next step you can take is modeling. So modeling is actually where you take your specification that you meant to be human readable and you make it computer readable. So you take your specifications written in English perhaps, some diagrams or something like that. You make like a Python model of it, and then you do simulations of your system, right? Or you make like a cock model of it and you do proofs about your system, right? And then finally, verification, which is kind of like, you know, the ultimate holy grail of being able to show that a design is sound, is where you build a formal enough model that you can actually prove that in all cases your model will never break. Like certain important things for your model to never happen won't happen. An example of this would be, you know, the trains don't crash, right? Or runaway inflation doesn't happen, right? So there's kind of like a bunch of different things you can do to mitigate these design vulnerabilities, but it all starts with specification, right? You have to write down what it is you intend the system to do. So code vulnerabilities are a little easier to understand for most programmers, but it's just where you make a bug in the code, right? You put a minus sign instead of a plus sign, or I don't know, you accidentally added something twice to the sum instead of only adding it once to the sum, right? Just simple code errors. You forget to use safe math when you should have used safe math, or maybe you're using safe math and you don't need to be using safe math, so you're wasting gas, right? So it's simple things like this, and this is a little more easy to understand. And of course, there are bugs that come from code issues, but this is a little easier to kind of, just spend time reading the code and say like, oh, okay, like I checked every single addition in the code, and I made sure that every single one that needed to use safe math was using safe math. Okay, then you're done, right? Like you've done all you can do for that. So code vulnerabilities are a little more kind of mechanical, cranking out the issues there. The design vulnerabilities and the design specification itself takes a bit more time and a little bit more of a creative process. So also, I'm sorry talking so fast. I had too much coffee probably, so. Let me know if there's questions. So mitigating code vulnerabilities, the simplest thing is just testing, right? So you just write tests, exercise your code, think about all the corner cases for all your different code paths, and you want to make sure that every branch of every if is exercised, every requires clause is exercised, stuff like that, right? And a lot of people write unit tests. Unit tests are great. I love unit tests. Please write lots of unit tests. But also regression tests are important as well, right? Like the regression tests are where you find a bug, maybe not through testing or through some other thing. You need to write a test that explains that bug and include it in your test corpus. That way that bug doesn't get reintroduced. And then another thing that I wish I had listed on the slide here, which I don't, is property tests. So if you guys have heard that term, property testing, so in Haskell there's a library called QuickCheck, and in Python there's one called Hypothesis. And I think for Solidity, you have like the DAP tools suite, and you also have Foundry. So these are like really good fuzzing or property testing frameworks, and I highly recommend that you guys try out these tools on your smart contracts, because if you do go for an audit and you hand them this list of property tests, they are going to thank you so much, because then they can just go and try to prove that those properties are true, right? You've already kind of done a lot of the work of specification for them. And then the next thing, of course, an audit. You can have someone look at your code, and usually a code audit consists of some sort of checklist that the auditor is going to go through. So they're going to say, go check every addition, go check every subtraction. Like and go check every place where there could be reentrancy, every call, every transfer, every there's a specific list of checks that have to be done. And then there's also just you're looking for code smells, you're looking for places where it could be gas optimizations in the case of Ethereum. So yeah, that's what an auditor is going to look for in a code. And then they're also going to try to show, if they're a good auditor, they're going to try to prove that your code, or they're going to try to show that your code faithfully implements the design that you set out to implement at the beginning as well. But there's different levels of audits. Like if what all you need is a code review and you're pretty confident on the design, then maybe you don't need that step, right? And then you want to do some sort of analysis as well. So this would be, if you've ever used tools like Slither, for example, this is a static analysis tool. It'll take your code and it'll kind of report back to you, hey, on line 117, you have a potential reentrancy. You need to inspect that. Okay, you go check out line 117, and you realize, okay, the tool is wrong. There's no actual potential reentrancy, but at least you checked, right? And so these analysis tools are usually looking for specific classes of problems and then just reporting them back and hoping that it's useful. And maybe 20% of the notifications you get back are useful, but still you went through and you checked every single one of them, and you made sure you did your due diligence basically on your code development. So we use these analysis tools in our audits, and to be frank, like they don't really find much that we wouldn't have found on our own. I think we have one example of something where it found something we didn't find on our own. But maybe they find it quicker. Maybe they find it day 1 instead of day 7 or something of you manually going through and doing this yourself. So, yeah, and then the final kind of, once again, the holy grail is verification. So that's going to be where you have a complete specification of all the behaviors that your code should have. And then you want to actually have a computer check, a computer or by hand, just by doing mathematical proofs by hand, check that your contract only has those behaviors and has exactly those behaviors, right? And so that's kind of the key thing here. Is only has those behaviors. There's no other behaviors that I've missed in my description, and has exactly those behaviors. So for each of those behaviors, it actually conforms to the specification for those. So that's kind of the holy grail. That's what we're strongest at with our verification, is this code level verification, but we're not usually offering that for all of our audits because it's time consuming. It takes a while. So I'll talk a little.
Mm-hmm. Yeah. Can you elaborate more about the properties test?
Property testing?
Yes,
Yeah.
what are they?
So if you take a unit test, right? So unit test, you're going to say something like, okay, suppose x is 3 and y is 7, and then I call f on x and y, and I should get back the value like 28 or something like that. Okay, now you want to say x is some random integer and y is some random integer, and I call f on x and y, and what I should get back is 3x plus 5y or something like that. And then what a lot of property testing frameworks will do is they'll pick random values of x and y for you, fill them in, and run the test for that instance and check the output. And then they'll pick another one and run the test for that instance. So it's a way to get it'll run it like 1,000 times on different values of x and y and check the final result for each of those different values. Does that make sense?
Okay, so it's like I try to understand what is the difference with unit test.
Mm-hmm.
It's like, what is the difference again between this and unit test?
Yeah, so once again with a unit test, you would say like x is 3, y is 7, call f of x and store it in z, and then assert that z is equal to 10, right? With a property test, instead you'd say x is something random, y is something random, call f on x and y, which are something random, and you should get back x plus y is what you say instead. And so then it will pick a bunch of random values for x and y and then check that you get back x plus y every time for those values. So it's a little bit broader of a class of tests because it can run it a few thousand times each time and just check, is it getting the correct result on every single one. Now, if you do property testing, don't only do property testing, also do unit testing, please. You need to explicitly have unit tests for each corner case, and then property tests are just something in addition. It's like, a cherry on top of the cake, right? So. But the nice thing about property tests is that they end up being kind of like a mini specification, right? They're like that property test describes the behavior that f function should have on all inputs, right? And so that specification can be useful for someone who's trying to do code analysis and wants to, for example, prove that f is giving you the correct behavior on output. Does that help? Okay. So things to look up there would be like quick check is like the original property testing framework for Haskell, and it's a really good one. And Foundry is a good property testing framework for Solidity. Yeah, okay, so what does an audit from runtime verification look like? Well, we take a verification-oriented approach, and that's opposed to like a testing or fuzzing or penetration testing style approach. And that basically just means we're trying to prove the correct operation of the financial protocol. And if some financial protocol, we're trying to prove that it's operating correctly. This is done in 2 steps usually. There's some sort of design modeling step and then a code review step. And there's, the lines get blurred between these steps, but usually you do the design portion first, then the code portion after, so that fixing things at the design phase is a lot cheaper than fixing things at the code phase. Yeah, so you do the design modeling. First, you formally describe the system that's coming up with your specification. Then you need to explicitly list all of your assumptions. And that's, once again, part of the specification. And you state important properties that you want to hold for the protocol. So, the amount of DETH never goes down, right? Like, that's an important property for this protocol, right? So we state that important property, and then we want to check that property holds, right? And then there's a code review phase where you're looking for common coding errors, like I said, checklist of things. And then you finally want to show that the code faithfully implements the design that you modeled in the design modeling phase, right? So that's kind of what an audit at RV looks like. And yeah, the most important, or one of the most important parts of this is the specifications that you need. So you need specifications in order to do verification. You need specifications to even be able to just communicate about things, right? We need to write down we need to write down very explicitly what is a slot, what is a knot, right? What is a stakehouse? What are all these things, right? You have to define these things. You have to say how they relate to each other. You have to say how they can be updated with each other. And there's a bunch of different ways to do specifications, but if you don't have time to do like a formal modeling thing, just write it down on paper. Make a white paper, do a pass over it, show it to your mom, show it to like someone else who has some programming expertise or something, and they're going to ask you lots of questions about it, and you're going to realize, hey, my specification's incomplete. Okay, complete it a bit, right? So you really want to make sure that you're thinking ahead of time about all those different cases that could happen, because it's so much cheaper to fix things at specification time than it is after 2 months of developing code, right? Like oftentimes we get a project and it's like, okay, we've already finished the code, time to do the audit, and it's like, you guys don't even have a white paper, you know, like what is it you're trying to implement? And we have to like pull out of their brains a white paper basically and write it down ourselves. But it would have been a lot cheaper, and they probably would have caught a lot of bugs themselves if you know, they had written down the white paper to start with and then gone to implementing the code. So yeah, that's kind of the specification's important. Please do it. So yeah, so now I want to talk a bit more about this specific audit report, which I don't think is public yet, but I think it will be public soon. And the audit report, like I said, I can answer high-level questions about our process. I'm not an expert on this particular one. I didn't do the audit. But the first thing, like I said, you know, specification is important. Being very clear about what exactly we did or didn't do is important. So we write down at the top what the scope is, right? So we say, like, we looked at specifically these contracts. We didn't look at these contracts. We assumed that Curve is operating correctly. We assumed that, you know, Uniswap v2 pools are operating correctly. So you make a bunch of assumptions about contracts that it's interacting with, and you don't, you say, like, okay, we're assuming that those are operating correctly, and if there's a bug in one of those, like, who knows if this one will continue to operate correctly, because that was part of our assumptions for this protocol, right? And it's important also to state which contracts you didn't inspect. And then you need to explicitly state the security model you're working with. And if the security model doesn't hold, then it may invalidate the results of the audit, right? Like if the whole entire way when you're doing the audit, you're thinking like, oh, the security model, we're making this assumption in the security model, and that might be something like, you know, if you're talking about beacon chain validators or something, it might be like this percentage of beacon chain validators are honest, right? And if that assumption doesn't hold, then all the rest of the results of the audit might not hold, right? So it's important to be very explicit about these assumptions. And then finally, you want to say exactly what you did methodology-wise, and this is for a couple reasons. The first reason is you want to be explicit, like, hey, we already ran Slither on the code. You run Slither on the code again, but you probably won't find anything else because we already did it, right? But another one is when things that are audited get hacked, you want to be able to go back to the methodology and say, what went wrong, right? Like where in our methodology could we have changed things and actually caught that issue, right? And so that's more an auditing firm internal sort of thing, which fortunately we haven't really had to do. But but yeah, I mean, it's important to be explicit about that methodology just in the name of transparency, honestly, just in the name of saying, like, this is what we tried, this is what we did, and then, you know, the client might say something like, well, why didn't you try this thing? It's like, okay, well, this other step in the methodology covered it already. Or, you know, you're right, like, let's try that and add that to the list of things we did. So this part of the audit report is about 3 pages. And then there's the modeling, the design modeling part of the audit report. And this is 24 pages. And it sounds big, but it's basically just calling out every different key component of the structure of the entire system and describing exactly what it should do. So this is like a white paper on steroids, or a more formal white paper, if you will. And so this is an example of an excerpt from one of these, and you can see, okay, we have some English description of what it should do. We got some links to exactly the contracts we're talking about. Earlier in the report, we fixed a commit hash for the particular version of code that we're working with, which is important because, you know, we have to be clear about this is the version of code we looked at. And then, you know, we have some invariants. So these are key properties that need to hold for the safe operation of the protocol. And if these properties don't hold, then, you know, you can't be sure that the protocol will be operating correctly. So these are what we're going to try to prove, these invariants, like the df supply never decreases. These are what we're going to try to prove about the protocol and about the code itself in order to show safe operation of the entire system. Does that make sense? Yeah, more modeling stuff. There was a significant off-chain component about this particular audit, and what this CIP, or Common Interest Protocol, and there's this Common Interest Manager thing, and there's some access control. But in particular, there's like these HTTP endpoints that need to be exposed. And, you know, we need to be explicit about that. We need to say, like, these have this amount of uptime, and, you know, these are going to be available for us to be able to make the queries and get, you know, information from, basically. So that's part of our modeling. And these assumptions, if the assumptions about these HTTP endpoints, for example, don't hold, then the rest of the audit might not hold, right? So it's important, if you're looking at a DeFi protocol and you want to assess its security, you need to look at these assumptions and these models and decide, do you think they're reasonable assumptions? If you don't think they're reasonable assumptions, then you probably can't trust the security model that's used for the audit, right? And yeah, that's how to read these, basically. So this is how to read an audit report is what this talk is turning into. Okay, so what is, like I claimed that we do like this verification-based audit report approach, or auditing approach, right? So what that means is that we write a specification down of what the protocol is supposed to do, and then we try to prove that the specification, or try to verify that the specification actually holds over the protocol and over the code itself. And so, for example, here we have the correlation between the beacon chain balance and the Stakehouse balance, which roughly means tokens in the protocol are backed by ETH on the beacon chain. Okay, that's a it's a ETH2 staking protocol, so that makes sense. But there's this invariant, assuming the knot has not been kicked, df plus 8 minus slash less than or equal to balance plus q, right? And that basically is just stating what I said in English over here. Tokens of the protocol are backed by ETH in the beacon chain. And we tried to verify that this was correct using a bunch of different techniques, right? By looking at the protocol, looking at the code, looking at stuff like that. And we found several major issues, basically. And so those are listed in the audit report. Issues A14, A16, A17, A18 were discovered in the process of trying to verify that this particular property holds over the code, right? So what does, like, A16 look like? So A16, amount of slash slot in the Stakehouse may be less than the amount of incurred penalties on the beacon chain. And so, we went and tried to verify this property about the DETH in the system, showed that it wasn't holding because of this issue, right down an attack scenario. So here we have an attack scenario where we're tracking like the active balance and the slot balance, and showed that the property doesn't hold. Okay, then talk with the Blockswap team. Blockswap team comes up with a fix and say, hey, the fix looks good. Looks like that particular issue is taken care of, right? And then once all of those different verification goals are discharged, right, then we can have high confidence that the original property that we wanted to hold actually does hold over the system, which is important because this is just a sensible property to have with the system, right? If you didn't have this property, you'd be like, what the heck's going wrong, right? So that's kind of the process there, right? You state a property you want to hold, attempt to verify it, and that's including whatever tools you need to use to do that. The verification fails because there's some bug in the code, there's a bug in the protocol, something like that. That's these issues A14, 16, 17, and 18. Then you got to figure out, okay, maybe our property was wrong, maybe our property was too strict, and that could be the case, or it could be that there was a problem in the code. So talk with the Blockswap team. They're very on top of answering our questions, and because we had a lot of questions, and there's very good back and forth dialogue between our two teams, and finally, came up with a fix, and all these issues were addressed. So that's kind of the process we're going through there. Another example is of a verification that needs to happen. All through smart contracts, there's this desire to use like floating point or real numbers or something like that, but we don't have access to that. What we have is integers, and we have to do fixed point integer implementations directly in Solidity for the most part. A lot of people kind of overlook this. This is really important. Like, I can't emphasize enough. You need to do precision analysis on your fixed point arithmetic, because like one of the original audits we did for Uniswap v1, we found a bug where due to loss, like rounding errors, because of how they were doing fixed point arithmetic, you can make a small change in the input amount you were putting for a swap and get like a huge change in the output. Actually, we were able to make it so, and there was an arbitrary change in the output just with a small change on the input. So you could basically set the exchange rate you wanted to arbitrary values just by playing with your input value of it. So I can't emphasize enough, precision analysis is important. And so here, for example, we took the fixed point arithmetic library that's used in the contracts, and we did a thorough precision analysis, and we showed, for example, that every time that these specific operations happen, the rounding error is towards 0 or something like that. And if you could show that consistently, then you can have in your mind for the rest of the code, okay, every time there's rounding errors, it will be towards 0, right? Is that safe for this particular invariant? So you might be looking at, for example, this invariant right here, assuming the knot has not been kicked, and there's a less than or equal to right there. So there's a plus and a minus on the left, and you have to think about the rounding errors that come with that plus and minus. okay, they're going to be towards 0, so that doesn't bother the less than or equal to, right? It's still going to hold for that less than or equal to, but then there's a plus on the right, so it might affect that less than or equal to property right there. So that's why these precision analysis things are important, is to, you do them ahead of time. You think of, you do an analysis of the precision of your mathematical library ahead of time. That way that's already in your head for when you're looking at the rest of the code. Yeah, precision analysis, that's kind of a nice part of the report. It's towards the end. Yeah, and then, so sometimes it's possible or it's desirable, or there's time to actually double check the result of some of the verification with tools. And so there's an example of that in this report, which is pretty nice. We took the save ETH registry and we made a simplified version of it that the Solidity SMT checker could handle. So Solidity SMT checker, if you haven't seen it, it's a very nice project. It gives you the ability to do model checking directly in the Solidity compiler, so you don't have to install anything other than the Solidity compiler and a SMT solver like Z3. And so we take the save ETH registry, make a simplified model of the save ETH registry, put it into the Solidity SMT checker, and then we check some important property about the DETH that's being deposited, not going down and staying above some other quantity or some exchange rate on the DETH. I don't understand the details, as you can probably tell. But anyway, so sometimes it's nice if you have some, key component of code, and it's really important that your property holds over that key component. Okay, go verify it with a tool. Like we already checked it by hand, go check it with a tool as well, just to make sure, right? Okay, so overall summary of the audit report. It includes everything we learned, right? Which, if we kept auditing for another 10 weeks, probably we'd learn more things, right? It has 66 pages. There's 24 A-level findings. Well, 66 pages of findings. I think it's like 120 pages of audit report total. But there's 24 A-level findings, which are usually going to be issues that definitely should be addressed or at least discussed. And 12 B-level findings, which are informative. So that could be like gas optimizations or other things like that. And when you're reading the audit report, our firm uses a 2-axis scale. We have severity, which is like how bad is it if this is hacked. So everyone loses their money. That's pretty bad, right? But something like people's money is temporarily locked for a day or something like that. Okay, that's maybe medium severity, right? Like people don't like that, but it's not like they're losing their money. Difficulty, how easy is it to make this exploit happen? And usually you're thinking about this like how much it costs to do the attack versus how much you're making on the attack. So if it costs 10 ETH to do an attack, but you only make 1 ETH, you're only going to do this attack if you really hate the person you're attacking. Like you're paying to destroy their protocol, right? If it costs 1 ETH to do an attack and you're earning an ETH to do an attack, okay, you only have to mildly hate the person to do the attack, right? But if it costs 1 ETH to do the attack and you're going to make 10 ETH doing the attack, well, you're going to do that just to make the ETH, right? Like, so that's what this difficulty scale is, if someone discovers that the attack is there, how likely are they to actually do the attack? Because there's some things that there's economic incentives to not do these attacks, right? And then there's a category, so that's going to be like code vulnerability, design vulnerability, incorrect use of safe math, things like that. And yeah, just for everyone's understanding, high severity but low difficulty findings are the worst ones. Those are the ones that definitely need to be addressed. Yeah, so the challenges with this particular audit, I mean, it was a really large system is the first part. Just quite a bit of code. That's why the audit took a long time. I think we're even over the 10-week timeline that we gave initially. And there's 9 different kind of main on-chain components in scope, which are listed in that scoping section, which contracts do we inspect and not inspect. And the methodology section talks about how we looked at them. And then this modeling section, there's 9 different components in this modeling section, including some of the off-chain components as well, like the CIP. So just the sheer size of this particular system was kind of a challenge. And then the other challenge is that there's a not insignificant off-chain component, this common interest protocol that allows transferring management of a knot. So yeah, I mean, you have to model this off-chain component because it's critical for the correct operation of the protocol, right? So we had to build basically just kind of a rough model in English of what this common interest protocol looks like. And in this description, there's a bunch of assumptions, basically, right? This is part of the security model. So there's a bunch of assumptions here saying, like, you know, basically that the operators of the knots are going to be competent, right? Like, they're not going to leak their private keys. They're not going to, you know, do other things like that. And they might seem like obvious assumptions, but it's important to state them, right? Because you, as a user of this protocol, needs to go and see, like, do I think it's reasonable that these operators won't leak their private keys, or do I not really trust them to do that, right? You have to make that decision yourself. All we can do is state the assumptions. Or you have to think, like, do I think it's reasonable that the C header library is implementing, you know, BLS crypto? Do you think they're correct? I don't know. You know, it's up to you. So that's kind of another one of the challenges, this large off-chain component. We had to just build a model, like kind of a rough model of that, so that we could understand how it was interacting with the on-chain component, and then state all the assumptions that we made of that off-chain component. Yeah, okay, so next steps. Security and software quality assurance in general, it's an ongoing process. Like, it's something that, you know, you should be thinking about from before you start writing the code. You should think about it while you're writing the code. And even after the code is deployed, there's things you can do to, you know, keep your confidence in the code's quality high. And so, like, before you're writing the code, you want to make sure you're doing the specification thing that I've been kind of talking about the whole time. You really want to make sure you specify things. But following an audit, you know, you can do runtime monitoring. So that's just watching the system and making sure that, you know, things are operating safely and within parameters, within tolerances that you expect. And then you can also, you know, a next step would be mechanized verification. Like, a lot of these these proofs that we've done are by hand. Mechanized verification is more expensive because it just takes longer. But the benefit you get there is upgradability. Like, if you upgrade your smart contracts, mechanized verification is where you take all these proofs we did by hand and you have a computer do them instead. So you have to translate them into some language that both the computer and the human can read, basically. And that's usually some mathematical language. And the nice thing about that is the computer's like giving you the green check mark, so you have like a little higher confidence that your proofs are actually correct. But the even nicer thing about that is you upgrade the protocol and the code changes. Maybe you just drop the code into the same proofs and the proofs go through still. Maybe, right? So maybe it works for like 80% of the proofs you did. And so then you only have to, you know, get the last 20% of them passing again to have the same level of confidence in your upgraded protocol that you had before. So that's kind of the value there of the mechanized verification. But I mean, you really should start thinking about software quality assurance from before you're writing the code, you know, thinking about like, what is it I'm actually trying to implement? Write that specification down, you know, talk to your mom about it. And if you can't explain it to her, then maybe it doesn't make sense, right? So, okay, that's all I've got. I'm open for questions. Once again, I'm not an expert on Blockswap itself, but I can talk about our audit process and stuff, so.
Can you explain a little bit about the formal modeling that you touched? How does that really help, especially with smart contracts? You mentioned about you losing a large amount of assets, especially in the case of E. We see that like 600 million, 300 million, 400 million every hack, right? Yeah. You lose that asset, and there's no way to get that one back. There's not USDC or some other coin that you can.
Yeah. Well, so I mean, once a hack happens, like the hack's happened, right? There's nothing okay, all the prep work you did wasn't enough, right? That's what it comes down to. But the reason that you're doing an audit, or the reason that you're going through like some sort of software quality assurance process in general, is to try to prevent hacks from happening, or at least push out the timeline that they're reasonable to happen. Because every system that you have, there's no way to say like the system is safe. You can't just be like, oh, okay, the system is safe. And that's because, you know, assumptions are changing, right? Like if you say like your train system is safe for the city, you add another track. Is it safe anymore? Maybe not. You have to recheck that, right? So, or for example, one thing that's closer to home for crypto is a lot of the audits weren't assuming, we're assuming that, you know, you had to have a large amount of capital to pull off some of these attacks, right? Then flash loans became a thing. And suddenly a lot of results from prior audit reports weren't valid anymore, right? And so, like, is this something the auditors should have thought about, or something you should have thought about? Maybe, right? But it wasn't there, so how could they have known about it? And so assumptions are changing around the system. So it's not like you can say like, this is safe and it will be forever, right? But what you can do is you can push out the expected time until an attack happens, right? And so that's the purpose of going through an audit, is you say, like, we're going to spend, 6 weeks or 10 weeks or whatever doing this really intensive review of the entire platform. And ideally what that means is that the first hack won't happen for 6 years, right? Or it won't happen for 12 years or something like that. So really you want to push out that expected timeline. And most of the times these contracts, the expected lifetime is pretty short. It's like 6 months, then V2 is coming out, right? Or 18 months, then V2 is coming out. So you only need to push that out like 2 years or something. But we're really we're trying to push it out to infinity, right? We're trying to push that expected hack time out to infinity. But it's to claim that we have would be a disservice, right? Like it's just not true. It's not how systems and code and programming and all these things work, right? So, but the reason we go through this modeling step in particular is actually because oftentimes not even the client has a good idea of what they're trying to implement, right? Like they've maybe sat down, written some code, gone through and, has some sort of white paper, maybe done some simulations or something, but there's nowhere written down exactly what's supposed to happen in every single case. And then you start writing down what's supposed to happen in every single case, and they realize, like, oh, I haven't actually thought about that case before. So you need to write that down. You need to write down explicitly what's supposed to happen in that case. And then you go check for that case, does the code do the right thing? You find it does something completely different, right? So that's the reason you go through that modeling step, is really to iron out what is the system supposed to do, if that makes sense.
Yeah. So, right. So you also showed another one is like the calculation of the particular validator values.
Which one?
Minus, the slash values. The invariant rule.
This one?
Yeah. So particularly, like, deals with most of the validators in consensus layer of the beacon chain right now. And you don't really get 10% of ETH is being staked, so we're talking about $300 billion asset.
Yeah.
That's good. If we have like 30-40% ETH is staked, and it's bridging over to ETH, to DeFi, whatever the process, it's going to ripple effect. And everything is like 30 to ETH is the unit. So currently, beacon chain won't give you this kind of per validator level inflation rewards that is being earned. But you can get it if you have BLSD, you know what is being approved to you, but it doesn't really expose that by default. So you have this kind of mechanism design in place to give the deterministic data. So how does, especially in kind of, like you mentioned Uniswap, you mentioned other things, mostly like the Stakehouse, these are contracts that don't use any oracles. Specifically those mechanisms. And so how important that when you do this kind of mechanism design to be tested to an extent that it holds?
Well, testing should be something that I think as soon as you have code up, you should try to start deploying to testnet, just so you have that in place and you can start poking at the system and trying it out. But if you don't test, you don't have, like, you can, one of the things about modeling is great, right? Like modeling, like you're getting it, you write down the what's supposed to happen, the invariants and stuff, but it could be that this invariant trivially holds because the system, for example, always just returns false and exits, right? Like, okay, then this invariant holds, right? So modeling is great, stating these invariants is great, but you need to actually be poking the system and trying it and deploy it to testnet and try actually setting up a Stakehouse, right? And actually try making sure that rage quit works, right? Like make sure that all these different components are actually working in the scenarios you do expect them to work in. And then you have higher confidence that, okay, my modeling actually is corresponding to something that's working in the real world, right? But the modeling phase itself is more for just getting that human in your brain level understanding of what's going on, how the system is supposed to operate, and making sure, and it's also about communication, right? It's like, I am talking to you, you're a developer, I'm an auditor. I need to make sure that we agree what a not means, right? What a slot means, what it means to rage quit, like these things need to be very clearly defined. And then we also need to go and check, like, is rage quit actually even possible, right? Like, so an example of this is like Black Thursday event when the price of ETH crashed, right? And multi-collateral DAI was working perfectly fine, and it continued to work fine through that crash, except the behavior had the system had unexpected behaviors, which were technically in spec, right? It's just that the it's just that the auctions couldn't keep up with the liquidations rate that were happening. And so the price of DAI went up to, you know, like $1.12 or something like this. This probably could have been discovered with some simulation, right? Like, and so it's just this, you know, modeling is great. Like the model said, you know, okay, the liquidations will be able to clear all the DAI auctions or something like that, right? But if there had been some simulations talking about like, okay, let's just take the price of ETH and tank it, right? And see what happens to the system. Okay, maybe that would have been discovered ahead of time instead of after that point. So I also think testing and simulation are great. So I don't know if that helped answer your question at all. Huh? yeah, exactly. Permissionless. It's participatory. we can all be the yield if we want. So, okay. Any other questions? Or I'm sorry I ended early, although I think I started earlier. So, okay. Well, thank you guys, and yeah, I'll see you around.